Okay, good. All right, so we left off pretty much in our discussion last time around here, and we were just commenting on how weak acids could have different strengths. So one weak acid could be stronger than the other, but they're both weak. Also, we were talking about relationships of their conjugates, and we were uh, just going back to the fact that there's an inverse proportionality between the strength of a weak acid and the strength of its conjugate base. And we made some arguments about why that should be true because of what we know about equilibrium. Uh, and when something is strong, strong acid, strong base, it's said to push that equilibrium to the right towards products. So anything on the other side has to be weak compared to the in this case, weak acid. So the stronger the weak acid, the weaker the conjugate base, in other words. Then we went on and we even calculated some things like pH for these weak acids. And I think that's pretty much where we left off last time when we were talking about these. And so now it seems like a pretty good spot to maybe try some problems and think about what's going on. So maybe you should take out a piece of paper and try these. Here we have two questions. The first one is, what's the pH of a 2-molar solution of these two acids? So how would we find the pH of a 2-molar solution of acetic acid? Anybody?
You're jogging our memories back to 152.
Yeah, I think I need a smack in the head myself. I got a lot of cobwebs up there today for some reason. It must have been a long weekend. Uh, yeah. So in order to find the pH of these solutions, we probably can start it at many different points. But I often like to start out with definitions. So first of all, what is the definition of pH? Anybody? What's the definition of P anything? Px equals, you guys don't remember that? All right, well, you got to memorize this. It's minus the log of that thing. It's just a mathematical definition. So pH would equal what? Is anybody there? Did you
Minus
guys
the
know?
log of hydrogen.
Yeah, thank you. I thought maybe everybody left. Okay, H plus. And we could represent that as H plus or H3O plus, depending on how lazy we are and if we want to include that into water into the equilibrium or not. Okay. So the question asks for the pH. So what are we going to have to find?
The H plus.
Yeah, okay, good. And so now we got to find the H plus concentration for each case. So for A, we have acetic acid. What's our approach for finding the pH of a 2-molar solution of acetic acid? Well, let me ask you, is it 2-molar?
No, because it's a weak acid.
Yeah. So it's not 2 molar. What is it? Something less than 2 molar, right? All right, now in Chem 201, we found out that things come to equilibrium, and that's why we need equilibrium constants to tell us the amount so we can quantify just how much that reaction takes place so we can find just how much product is produced. So for this acetic acid, I'm just going to give it the generic HA name for some monoprotic weak acid. And I can add that to water, or it's aqueous, so it's got lots of water in it. And I know it comes to equilibrium at some point. And I form H3O plus the conjugate base A minus. And the H3O plus, that's the thing that we want to find because that's what the concentration of H plus equals. So how do I find that? Anybody? I know it's not 2 molar, it's something less.
Would you use the Ka value?
Yeah, in an ice table. Awesome. So I'm going to set up an ice table because that's what we do in Chem 201 when we have situations that don't go to completion. They're not completion reactions. They form equilibrium, so you have a mixture. So I can put this 2 here initially. I don't have to worry about the water because it's already incorporated into the equilibrium constant. I assume that when this was made initially, those products were 0, but then I formed some as time went on and the reaction goes to equilibrium and I lost some HA. So now I have my ice table all filled out and I see that in my ice table, if I could find X, then I'll know how much H3O plus is produced and I'll be able to solve for the pH. Okay, any questions so far? All right, so what do I need now to find X? If you don't ask me questions, I'm going to ask you guys questions.
Ka.
All right, and where do I find Ka?
It's on the table like a couple slides back.
Yeah, it's in your textbook or it's online or something. And so I got to look that up, and I think it's about 1.8 times 10 to the minus fifth because it is weak. And I know that according to the law of mass action, this should equal the concentration of the products to their stoichiometric coefficients over the concentration of the reactant, in this case 1, to its stoichiometric coefficient. And these are all equilibrium values, so it's x times x, or x squared over 2 minus x. So now I have my mathematical equation to allow me to calculate X, which will allow me to associate that with H3O plus, which will allow me to calculate the pH. All right. So I'm going to do that. I'm going to calculate what X is, and I can do it using the quadratic, but we also said that if X is less than 5% of what it's added to or taken away from, then I can ignore it. And if I ignore it in this case, then I won't have to solve the quadratic. I'll just have to do a square root, which is a lot easier. So I'll neglect X here, say it's 0, it's negligible, and then I'll check the 5% rule to make sure that that's true. So I get 1.8 times 10 to the minus fifth equals X squared over 2. So I multiply both sides by 2 and then take the square root and I get X. And you guys should try this with your calculator to make sure everything is cool and that I didn't make a mistake. Minus times 2 square root. So I got for x 0.0060. Did anybody else get that?
Yeah.
Okay, awesome. All right, so I have to check the 5% rule. So what I'm going to do is I want to see if 0.006 is less than 5% of 2. That's what I neglected it from. And so I get divided by 2 times 100. I get 0.3%. And so that is less than 5%, which means that if I did solve the quadratic, I would still get the same value. So I just had, I got a nice shortcut. I didn't have to worry about the quadratic. And now I can take that and I can calculate the pH. So the pH is going to be minus the log of 0.006, which is going to be 0.006 log. I get 2.22. And that's to 2 significant figures. All right. So you should also realize that's 2 sig figs, because once you take the log of something, and that's base 10 or the natural log, what you generate is something else that's not a number like we think of it. The thing that you generate has what's called a character, and that's to the left of the decimal. So this is the character. And that's the power of 10 holder. And to the right of the decimal is called the mantissa. And the mantissa, that represents all your significant figures. So this is just a mathematical fact that you might remember. If not, you can look it up, but you should remember it now. So when I take a pH and I want to find the concentration from it, then I have to reverse it. I have to recognize that this pH is unitless. It's not like a number that we're used to thinking about. It's made of a character and a mantissa, and it shows 2 significant figures. So when I inverse it to get a concentration, then that concentration can only have 2 sig figs, like what it came from. Any questions on that? So in other words, pH equals minus the log of H plus. And if that equals 2.22, and I want to calculate what H plus is, then I have to take the inverse log of both sides. The inverse log of both sides is 10 to the whatever. So if I do a 10 to this, then I have to do 10 to the other side. That'll get rid of these. And let's bring that negative sign over here from here. So H plus is going to equal 10 to the minus 2.22. And if you punch that in your calculator, it should come out to, I hope, 0060 or whatever it comes out to. Let's see. Yeah, and my calculator says 0.006, but I know that it has 2 significant figures, so I have to add that last 0. All right. Any questions on that? So you got a little lesson on mantissa and character and pH and how it's not a number, but when you use it to get your concentration, you're converting it back to a number. And so you have to maintain those significant figures. It's kind of like, well, it's what I said. So if there's no questions on that, then we're good with the acetic acid. We have its pH. All right, how about nitric acid, B? How are we going to find that?
You'd do the same thing. You'd find a Ka value and then rate it to relate it to the equilibrium.
Okay, so if we try that approach, we're going to try the same thing. What is the Ka? Can I find the Ka of HNO3? Anybody find that in their textbook or online? I can't find it. Anybody know why?
Is it a strong acid?
Yeah, it's a strong acid. So it doesn't have a Ka. So this problem is easier than an ice table. For this problem, since it's one of the 7 strongs that you have to memorize, then you know there's really not an equilibrium. It's a big arrow that way, microscopic the other way. So we get H plus completely 100% and NO3 minus. This is very different from the previous case of acetic acid where it's a weak acid and it's nowhere near 100% dissociated. In fact, it's less than 5% dissociated. We use the 5% rule. That X is less than 5% of 2. So the equilibrium in that first case lies way to the left, whereas in a strong case, in a case in Chem 200, it's way to the right. And we know that for 2 molar HNO3, we don't have any HNO3 and 2 molar HNO3. It sounds funny. We don't have any HNO3 in there. It's all gone. We have 2 molar H plus and 2 molar NO3. So it's really easy. The pH then, we just calculate it as minus the log of 2. So I think that's even negative. I'm not sure. Let's see, 2 log, yeah, it's minus 0.3. And that's all I could write because that's one significant figure in 2 molar. Any questions on that? So you see, you don't want to fall down that rabbit hole because if you go down the wrong path, you're going to run into problems that you're not going to be able to solve. So I guess the moral of the story is okay. Any questions on 1? All right, number 2. This is an interesting problem also. Now, what if we take those 2 solutions from 1 and we take 50 mils of each and we put them together, we mix them? What's the pH of that mixed solution? And how would I even go about finding that? Anybody have any possible approaches to do this? How are we going to do that?
Would you start by using the concentration of the H pluses, adding those together and dividing them by the 50 milliliters to get a molarity?
Sure. Okay, good. So what we would have then in that case is we would be taking 2 molar 50 mils and increasing the volume to 100 mils, essentially halving the concentration. So now once they're mixed in the mix, we have 1 molar HA and 1 molar HNO3. Awesome, very good. All right, now where do I go from here? I think you were implying that we should find out the H plus concentration from each and then add them together.
Wait, sorry, how did you figure that it was 1 molar of each?
Oh, it's just a dilution. It's a dilution law. So you remember M concentrated times V concentrated equals M dilute times V dilute, the dilution law. So if I take 2 molar and I take 50 mils of it, what is the diluted concentration? And there's going to be 100 mils total. So M dilute equals 2 times 50 over 100, or a half. Okay, thanks for asking. All right, so good. We have 1 molar solution of each. We just diluted them with each other. And I think somebody implied that we could calculate the concentration of H plus in either case and then add them together. But the answer, as you're going to see, hopefully, is that it's easier than that. When you mix a strong acid with a weak acid, the amount of protons you get from that weak acid is negligible compared to the strong, so you could ignore it. And the pH of that solution is just going to equal minus the log of 1, which is the concentration of HNO3, which is 0. All right, now let's see why that's true, why you can ignore the weak acid. Well, you know that the strong acid, HNO3, that's going to go to H plus NO3 minus. So I have 1 molar H plus. And that's it for that. Now, the weak acid, the acetic acid, HA, in equilibrium with H plus A minus. If I set up an ice table for this, it would look something like this. And check it out and correct me if I'm wrong. But if I just had a 1 molar solution of this, then I could get something like that. The Ka expression equals 1.8 times 10 to the minus 5th. That equals x squared over 1 minus x. So I can calculate x squared and then add it to the other one, which is 1 molar, and it would be negligible. And we know it's going to be less than 5. But that's not really the true situation, because once I mix it, this ice table is wrong somewhere. Can anybody see where I made a mistake in the ice table? I'll give you a clue. It has to do with the initial. No one see it yet? All right, I'll give you another clue. It has to do with this 0 right here. Is that really 0?
I'm unsure why it wouldn't be 0.
Well, because it's in the presence of a 1 molar HNO3.
So it would be a 1 since that HNO3 fully associates.
Yeah, exactly. Now that puts them together. That puts the two situations together. We said the strong acid, there isn't any of that left. There's just 1 molar H plus, right? So when I have that weak acid, it's not going to be 0. There's already 1 molar H plus from the strong acid that's in there. Now, what does Le Chatelier's principle say about where that equilibrium is going to lie in the presence of 1 molar strong acid HNO3? Will it shift? You remember Le Chatelier's principle?
It would still lie to the right now.
Well, let's say we let that go to equilibrium in pure water. And now instead, I'm going to add in that nitric acid. And now it's not pure, but it's 1 molar. So now I have a stress on the equilibrium, right? The stress is too much H plus. Which way does it shift?
Left.
Yeah, to the left. So in the presence of the nitric acid, is X going to be bigger or smaller?
Smaller.
Yeah, it's going to be smaller. And so that means you're going to get even less H plus from the weak acid when it's in the presence of a strong acid. That's what Le Chatelier's principle says is true, and that's what happens. So it's going to become even more negligible. X is going to be even smaller than it would be if it was disassociated in pure water, which it's not. So, I mean, we can figure out those two X's and compare them, but in either case, when you add them to 1, it's going to be negligible. So let me finish this out here. So I'd have a 1 plus X in this situation. And so this isn't true anymore. I would have 1 plus X times X over 1 minus X. Let's neglect these two X's, check the 5% rule, which I'm not even going to check because I know it's not going to be larger than 5%. And so now I see that X, this whole thing is a 1. So X equals this value. And so 1 plus 0.0000018. That's pretty much 1. Okay. Any questions on this? All right, you were just introduced to what's called the common ion effect, which we're going to get into. This is like a foreshadowing. We're going to get into this a little bit later when we start mixing solutions. and finding pHs. You have to identify which solution is going to give the equilibrium in the ice table, and then you have to see what the other solution brings into play. And sometimes if it's an acid, then that's not going to be zero. But what if it was like a sodium salt? Then that wouldn't be zero. It could be mixed with Na, some sodium, which I know from my solubility rules is completely dissociative, with some A. In this case, it would be acetate, but it could have been, if it was HF, hydrofluoric acid, then it would be F minus, right? That's what A is. And so you get a whole bunch of situations now where you might not have zero initially, and the X's that you're going to calculate after are going to be less because of this, what's called a common ion effect. And it goes hand in hand with thinking about equilibrium from the point of view of Le Chatelier's principle. So it's all tied together. Anyway, let's go on, unless you want to talk about that a little bit more. Okay, we're going to get back to the common ion effect in a minute. This next slide you should study. And what I tried to do with this slide is just to dissect the ice table. So you have the initial amounts, which sometimes are given in a problem, or you have to assume that they're zeros if they're not given, or you have to calculate them like you're doing in the equilibrium lab right now. You take the volume times the density divided by the molar mass, and that gives you the moles. You divide it by the total volume, you have its concentration, and that's how you can calculate these initial values. And then next in the ice table is the change column, and I put plus or minus for each one of those with the stoichiometric coefficient. Now they're plus and minus because in general, you have to figure out which way the reaction has to shift to reach equilibrium given those starting amounts. So if you have all the starting amounts, then you can form a Q, the reaction quotient, and compare that Q to K to see where the negatives go, whether they go underneath the reactants or they go underneath the products. And then you add them up, you have the equilibrium concentrations, and it's the equilibrium concentrations that you can relate to K and the law of mass action that tells you how to form those equilibrium constants. And in this case, it would look something like that. All right, so you should look over this, study this plate, understand the little ins and outs of the ice table, because the ice table is going to help you relate any reaction that comes to equilibrium. These are for equilibrium reactions, not completion reactions. Equilibrium reactions is going to help you relate those equilibrium concentrations to the equilibrium constant from the law of mass action, as well as the other things we talked about, like the reaction quotient. That's going to be formed with usually initial values. That's the first line. The pH, we talked about that definition and how we can relate what's in the equilibrium ice table to values that we need to define the pH. Solubility is coming up when we talk about insoluble salts. So that's going to come into play. Percent ionization and percent dissociation of some reactant. And we're going to talk about those too and how they are related to the ice table. All right. Moving right along, unless there's a question or concern, you can study that. All right, now this next plate introduces a problem that you might see in the textbook. And it says the pH of a 0.1 molar solution of formic acid is that at that temperature. What's the Ka in percent dissociation of the 0.1 molar acid at that temperature? And so it gives you the answers. The percent ionization or dissociation, which is the same thing, is that, excuse me, and the Ka is found here. So I set them up and I gave you the answers, but what I want you to do when you go back and study this is I want you to write out the ICE table and show that these answers are all true using the ICE table and the definitions that you find for the percent ionization or dissociation, the definition of the equilibrium constant, and then we move on from there. So when you go back and study this, see if you can set up the ICE table. What I'm going to do, though, is I'm going to skip through that and take a look at really briefly some problems that do what I just told you to do. And here we have example 1. What's the pH of a 0.2 molar solution of HCN? And that's all the problem will say in your textbook. So the way that you approach this problem is the first thing you do is say, okay, I know what the definition of pH is. It's equal minus the log of H plus. So I'm going to need to find that concentration of H plus in a 0.2 molar solution of HCN. The second thing is I recognize HCN as a weak acid because it's not one of the 7 strong that you're supposed to memorize. So it must be weak. So I know that I need to look up an equilibrium constant in order to find this X in the ICE table. And so you look that value up, and it may be given to you in a problem or not. You might have to figure out that you're going to have to look it up. So then you can set up the ICE table. You know this is one of these equilibrium problems, so you need an ICE table because it's a weak acid. You put in the initials, and you solve the ICE table by relating what you get at equilibrium to the equilibrium constant that you looked up and its definition using the law of mass action, which says concentration of the products to their stoichiometric coefficients over the reactant to it. So you see that it's going to equal x squared over 0.2 minus x. I can use my 5% rule and check that. Simplify this, find x, and then find the pH. So that's kind of the thought process for this approach, which I'd like you to practice. So maybe, in the last one, I didn't set up the ICE table for you, so that's good practice. When you go back and look at this, you might want to hide this, right? Just hide that, look at the problem, and then see how you're going to figure this out. Go through that thought process. And you have to first figure out what you're dealing with before you go down a path of no return. Any questions on that? All righty. This is the solution to that previous problem. So you should hide this too, figure it out, and see they go back and they check out the 5% rule to make sure that that X over here was in fact less than 5% of what they neglected to subtract it from, which is the 0.2. So to do that, you just take that X that you find from neglecting, you divide it by 0.2, you times it by 100, and you see that it's way less than 5%. So if you would go and do this problem using the quadratic formula, your answer wouldn't change. And if you don't believe me, go ahead and try it. All right, so far so good? All right. Like I said, if you have any questions, just yell or interrupt. Don't worry. The next few slides go into a little bit more detail, the 5% rule. So here's another case, pretty much set up the same way as before. We have a weak acid, we have its Ka, and we have its concentration. So we go ahead, set up the ice table. We look at the relationship between the Ka and the ice table, and we neglect that X to check the 5% rule. So we neglect it. That simplifies our math. We solve for the X. We go to check this 5% rule. And so we have to divide that by what we neglected to subtract it from over here, times it by 100, and we see, uh-oh, it's too high. It's above the 5% rule. Not by much, but it is above the 5% rule. So we can't use this answer 0.0082 for X, and therefore we can't calculate the pH from that. We have to go do the quadratic. So let's see how the answer changes. That's on the next slide. So we see that when we do the quadratic and we calculate X, it does in fact change from that 0.00, what was it before? 82 to 0.0079. All right, so the pH is going to change a little bit. And it only changes a little bit because we're just over the 5% criterion, but it does change. And so you have to keep checking. Now, having said that, most of the problems that you're going to deal with in Chem 201 from this point on are going to obey the 5% rule. But you should check it anyway. Any questions on that? All right, this next plate moves on to something different but related. It turns out that the percent ionization of a compound decreases when the concentration increases. And we kind of glossed over a little bit what percent ionization is. So maybe we should take a look at a problem. And we can make one up from this slide. It says for acetic acid, 0.05 molar solution is 2% ionized, whereas a 0.15 molar solution is 1% ionized. So let's make up a problem and ask ourselves, let me insert a slide. What is the percent ionization of a 2.3 molar solution of acetic acid? Okay, so you might see something like that. So I want to find out how much or what the percent ionization is. And they're talking about the acetic acid. So how should I think about this? Well, I know what acetic acid is. It's a weak acid. So right away, I can write a reaction involving acetic acid. I'll just call it HA. It's any monoprotic weak acid. So this could be any weak acid. It could be hydrofluoric, citric, propanoic, and so forth. Any one of the acids that's not one of the 7 strongs. So I know that this comes to equilibrium in water. And so I've neglected to put what it's in because pretty much that's all we've been talking about is aqueous solutions. And this whole chapter is all aqueous. But anyway, if I want to calculate the percent ionization or the percent dissociation, which sometimes are used anonymously. So ionization and dissociation are used interchangeably. What am I specifically talking about in this reaction? See if somebody can figure this out. What's the percent ionization of what here?
How much of that acetic acid is actually going to ionize into H plus and A-?
Yeah, so how much of that HA, the acetic acid, ionizes? How much goes into ions? And what is the percent? So what did I start with? The ice table kind of helps you. But anyway, how much acetic acid did I start with? Anybody?
2.3 molar.
Yeah, 2.3 molar. And if I put an ice table here, then I would put 2.3 here, 0, 0, x, 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 x. I'm just filling out the ice table, minus x, 2.3 minus x. So here I have all my ice table filled out. What is the parameter in the ice table that's going to tell me the amount of HA that dissociates or the amount of HA that ionizes? What's that parameter in this ice table that tells me that amount?
Is it the Ka value?
Well, that's how I'm going to find it. But what in the ice table here? In other words, for every 1 HA I lose, it ionizes. And it makes 1 mole of H plus and 1 mole of A minus. So if I want to find the percent ionization or the percent dissociation, I'm going to have to divide the amount that breaks up or ionizes over what times 100.
It would be over 2.3, the original.
Yes. The original, and what you said was 2.3. So my question is, what is this, the amount that ionizes? Is that in the ice table?
Is it X?
Yeah, it's X. For every one of these guys that break up, I get one of these. So X is the amount that HA breaks up, right? So that's what percent ionization or dissociation means. It's exactly what it says, right? How much of that breaks up, the ice table tells you. So this is how the ice table will help you relate to things like percent ionization. So how do I find X? It's the same way that you've been doing it before for finding pH. You use the Ka expression. So the Ka for acetic acid, we know is 1.8 times 10 to the minus fifth. That has to equal X squared over 2.3 minus X. We neglect that, calculate X, and then I can put it in here. Notice it's the same formula for the 5% rule, checking it. For checking that 5% rule. So percent ionization oftentimes is the same thing as checking the 5% rule. You're just finding out what percentage of that weak acid is breaking up. So don't get all kind of confused. Oh no, that's a new thing. It's percent ionization. Not really. It's the same old thing. In fact, its definition is in its name. All right, so we can do that. And I don't know if it's worth doing, but the previous slide, what it's saying is that as this value goes up, as the concentration goes up, what happens to this value over here, the percent ionization?
It decreased.
Yeah, it decreases. And so it kind of should make sense, right? Because this is the value right here in the denominator. So as that value goes up, you would expect this value here to go down. So mathematically, it makes sense. And that's the trend that we find. So you guys are going to be working up a pH and buffer lab when we look at that soon. And you're going to be looking for trends of percent ionization with concentration. So as you see the concentration of a weak acid, for example, increase, as that concentration increases, you should find that the percent ionization decreases, and look for that trend. If it doesn't, then that's an indication that you probably calculated something incorrectly. All right, any questions on that? All right, moving right along to other concepts in this chapter. We have to look at polyprotic acids. Some acids have more than one proton to give. And if you look at this plate of all these different weak acids, I know they're weak acids because the Ks are much less than 1, except for 1, and that would be sulfuric acid. And that's only for that first deprotonation. So each deprotonation has an associated equilibrium constant. Ascorbic acid has 2. Citric and phosphoric acid have 3 protons that it can give up, right? What do you notice about the magnitude? Remember, that's the number of the equilibrium constant for successive deprotonations. In every case, what's true? For
It gets
example,
smaller?
yeah, go ahead.
Oh, it gets smaller.
It does, it gets smaller. So the first deprotonation of ascorbic acid, 10 to the minus 5th, the second one is 10 to the minus 12th, which tells me that it's harder to take off that next proton than it was the first one. And that's true in every case. So when you have to calculate the pH of these different acids that are polyprotic, it's advantageous to know that whenever the subsequent K is 1,000 times less, that's a 10 to the minus 3, less than the previous, you can ignore it. It's not going to contribute to the pH. And that's pretty much the case for all of these. So this is an argument that says, well, yeah, maybe some acids are polyprotic, but if under normal conditions you want to calculate the pH, you really only have to consider that first deprotonation. So that's one thing that's said here. Now, that's not saying that you're never going to use the Kas of successive deprotonations. You might, because you might start out with, for example, oxalic acid. Instead of having a 1 molar solution of oxalic acid, what if you had a 1 molar solution of NaHC2O4? Then you know from solubility rules that you'd have 1 molar HC2O4 minus, and that's going to react with water, and it can react as an acid. And form C2O4 2 minus plus H3O plus. And this has a K equaling 6.4 times 10 to the minus fifth. And you can calculate the pH of that solution by writing out a nice table and using the appropriate K for that situation, which is the second deprotonation. Any questions on that? So it's kind of like a, a foreshadowing into possible problems involving the second deprotonation and using different Ks. But now, if I wanted to calculate the pH of a 1 molar solution of oxalic acid, I wouldn't have to worry about that second deprotonation. And the reasons involve that common ion effect that we were just talking about, because you already have a concentration of H plus from the first proton. So the second one is even less likely to deprotonate or deprotonate as much because of the 5% rule. So, that common ion effect is going to be pushing it back towards the equilibrium, and the second deprotonation is just not going to be important, like we found when we had the nitric acid in the presence of the acetic acid. We just ignored the acetic acid. It just didn't make a difference. So if there's no questions, I'd like to stop there. We'll pick this up again tomorrow, and I'll have something to say about that problem number 23 on the exam, whether we're going to keep it or not, to see what's going on with that.
I posted a scribble in the chat. I think what we were trying to do earlier was plug the rate into the concentration. But if you follow the units, then you basically just plug the given K constant and the concentration, initial concentration of NOBR squared to find the rate, and then you just do rate times time.
Yeah, that sounds like a possible solution. You just do rate times time. Let me think about that and see what assumptions have to be made, because let me think about it. That sounds reasonable. Okay. All right. I'm going to take a look at that, and like I said, I'll let you guys know what I come up with tomorrow morning. Anybody have any questions for me? You're just going to take off. All right. Have a good day then. See ya. See you later.
Thank you.
Paper.
Yep, thank
I
you.
did have a question for you.
Yeah.
It was about possibly setting up some office hours, maybe like once or twice a week to go over that last exam. 'Cause I did pretty bad on it.
Oh, okay.
So
All right.
if I can, I'd like to set up some meetings and maybe we can just go through some of the ones I struggled